Hello everybody! So, for today's video, we're going to be talking about vector fields and line integrals. So, these topics are getting slightly more advanced. They will show up a lot more often within applications and for further mathematics. So make sure you pay attention and try to understand what these things are. First thing, the vector fields. What's the definition for them? Well, let D be a region in Rn. So n-dimensional space. It could be R2, R3, whatever. Depending on what you're working with, R3 is probably going to be the most you'll deal with. If you're going into some certain fields, you might end up dealing with a lot bigger. A vector field on Rn is a function f that assigns to each point in the region an n-dimensional vector f of x1, 1. Alright, so that sounds weird. So let's take a look at a couple pictures of them. So for a two-dimensional vector field, this would be an example. So at this point, it's assigning this vector. So it gives you an idea of what's happening. So it can be a little odd, but it's a useful tool to look at, see what's going on overall. Now, for 3 dimensions, you have something that can look like this. So you have to keep in mind that they go in 3 dimensions because it's now a 3-dimensional space. When you're trying to draw shapes, though, keep in mind we have our gradient vector that we've talked about before, which is perpendicular to our shapes. Which means if we're dealing with a gradient vector field, all these vectors are perpendicular to our shapes. So these points are all radiating away from the origin. Well, if you draw a shape that is perpendicular to all of them in an area, well, guess what? That's going to draw a sphere. So this would be a vector field for a sphere. And then you have something similar going on here. You'd have a line going straight up. You'd have a line that curves off this way. And it might even come back around. So these can give some odd shapes. Just keep in mind that vector fields themselves, while useful, you have to keep an idea of what's going on with them and how to draw and to shape accordingly. Alright, so I talked about how these have applications before. Where do they get used? Well, ocean currents. That's a big one. Whenever you're looking at a map of the currents in the oceans, that's a vector field. Similarly, wind patterns, because they have the same type of setup. And for a lot of you, if you end up going into any aeronautics, your wind tunnel experiments, that's what you're looking at, a vector field. Gravitational forces, so anybody doing with aerospace stuff, guess what? You have to take into account the gravitational forces that are around. Might not be as big for you, but it still occurs. Electrical forces, these have a fairly major field as well. Because depending on your material, they might not want to go through certain areas. So those are some of the places that they'll get used. So we'll look at a few more examples of it tomorrow or in class. So let's not worry too much about that yet. Now, the other aspect for today's video, line integrals. So quite often it'll be a case where you want to integrate over a curve instead of an area. This is possible to do. Now, if we're looking at this, there are situations where you will want to do this. Because there's certain paths that you are looking at and determining what's happening along that path. And if you end up getting further along in mathematics, you'll end up often integrating over a curve that's surrounding a region. And we'll talk about that in a little bit on one of the later videos. Alright, so how do you define a line integral? Well, if you have a function that you want to integrate, and you have an equation for a curve, for the curve you want to integrate over, and let's assume that t is going from a to b, then this is the equation for your line integral. So we're back to a single dimension. And hopefully this isn't too hard. It's just the magnitude of the gradient vector and multiplied by your function there. Okay, nothing too bad. Now, one assumption for this. It assumes that it's a smooth curve that you're integrating over. Why does it assume that? Because if it's not smooth, these might not exist, and therefore you can't do it. So always keep in mind it's a smooth curve that we're dealing with for line integrals. All right, see you in class.